Hello everyone and welcome to my lab. I promise you a good time, an exciting time, especially if you pay attention and if you notice that I will be doing a lot of experiments and I will be obeying all the safety rules, including having my goggles on. And of course I have a fire extinguisher ready to be used just in case something goes out of control. We're not planning on anything going out of control, and this fire extinguisher will be just here. I'll take it out of your view so that you get to see everything very clearly. You noticed, of course, that the balloon I brought in had in it a gas lighter than air, as do all the other balloons that I have. That balloon had in it the gas hydrogen, and hydrogen combines with oxygen when the mixture is ignited in a very explosive way. What I'd like to do is show you that same chemistry reaction in the dark. So if we can turn the lights down, we can look at this balloon now, and I bring the flame to it, and with the lights on, did you see that ball of fire? What color was it? Yellow, orange, red is what I hear now. Did you hear sound energy being released when the explosion took place? Yes. What I'd like you to do now is look at that same reaction in slow motion. So let's look at this. You won't hear any sound. There's the flame, and there's the balloon about to be there. There's that ball of fire. And of course, we don't hear any sound as we look at this in slow motion. So we learn about the explosions differently as we look at them with the lights on and with the lights off. Let's see if I go on now to this balloon over here. Now, I notice some of you are covering your ears. It's because you learned that there might be some sound energy released. So let's try this balloon, and what happened? The balloon popped, but there was no fire. The flame went out, so I'll relight this torch here. That balloon had in it a gas lighter than air, and that gas is helium. So helium is a gas that does not burn explosively or doesn't burn, period. So let's go on now to the other balloons that we have, and we'll see what happens as I put the torch to this balloon. Ready? Some of you are covering your ears again. All right, here we go. Now, that was a different gas. That's a gas also lighter than air. And I will tell you that gas is called methane. That gas combined with oxygen in an explosive way, but the loudness of the explosion was not as great as it was in the case of hydrogen. So let's repeat that last experiment in the dark and look at this balloon now as I bring the torch to it. Ready? Here we go. With the lights back on, you were able to see the light energy that was released from that combustion reaction between methane and oxygen in the dark. Let's look at that in slow motion and see if we can learn more about the size and the color of the flame. You like that? Yes. Well, thank you. Now, we have one more balloon. We can leave it alone, or we can do something with it. What shall I do with it? All right, all right. One of the things we learned today is that when balloons are ignited, there may be a lot of sound energy being released. So I would like everyone to protect your eardrums before I do this last balloon by taking both fingers and putting them in your ears like so and push very hard. Now, I can't do the experiment and do that at the same time, so I have with me some earplugs which I will use. So I would like you to protect your ears by putting both fingers in your ears, and do that right now. If you can hear the sound of my voice, that means you don't have your ears well protected. Now, I can't hear you, but I can see you smiling. That means you heard what I just said. So please protect your ears as we go to the next balloon and do it in the dark? That balloon had in it a mixture of hydrogen and oxygen. And that mixture is very, very explosive. There was more oxygen available to the hydrogen to combine with, and that's why we heard a louder report and we saw a different color flame. Let's look at that last one in slow motion again and see what we can learn about that. There's the torch coming to the balloon. A much faster reaction, and the color of the flame, of course, was different. So chemicals, when they burn, they produce light energy. They also produce sound energy. There's so many different ways to produce sound. For example, I can take a glass rod and tap on glass vessels. That's one way of producing sound. Or I can just knock on the tabletop. A lot of different ways to produce sound. For sound to be produced, we have to have a vibration. In fact, you hear my voice because my vocal cords are vibrating and pushing the air, and a sound wave is reaching your eardrum, and then a signal goes from the eardrum to the brain. That's how we hear. There are many things that vibrate. Here is a piece of rubber that's been stretched and held in place by 3 nails. And if I pluck this, all I'm doing is producing a vibration that causes sound to be generated, and we hear the sound. There's so many other ways to do this. For example, if I take a whistle and I blow into it, there is a sound wave being generated because the column of air is vibrating inside the length of this whistle. In fact, if I take a piece and extend the length of the whistle, you hear the difference? And if I extend it even more, so the longer it is, what happens to the pitch? The pitch goes down, right? So let's do that. So that's one interesting thing that we want to keep in mind. The longer the tube where the air is vibrating, the lower the pitch. For example, I have this tube, which is hollow. If I blow in it, I just blow air. But if I twirl it like this, hear that? There are so many different ways to produce sound, and to help us understand and appreciate that a bit more, I am right now going to call on a group of talented individuals to help us understand what's going on. So here comes Todd, followed by Brian, Mandy, Fred, and Penny. Remember now, to have a sound, we need something that vibrates. And this something can be a stretched piece of rubber, or it can be a stretched piece of plastic. For example, that's what Todd has. And to produce the sound, we can hit it gently, or hit it a little bit harder. And the loudness of the sound depends on how hard we hit it and on how much the plastic film is stretched. So, Todd, give us a drum roll and see. It sounds pretty good, huh? Like that? Yeah? So that's one way of producing beautiful vibrations. Let's see if we can listen to other vibrations. Mandy, can you pluck one string on your cello? How about plucking another string? A third one? A fourth one? Now, can you pluck them all very quickly? Faster, as fast as you can. Actually, there is a way in which she can even pluck them much faster than that. That is to use the bow that she's holding. The bow is made of horsehair, and some rosin has been put on the horsehair so that when she pulls the bow across, then she will pluck all 4 strings at the same time very fast. So, Mandy? You like that? Huh? Remember, we can generate sound waves also by moving columns of air. And that's what we have now in the tube that Fred is holding. What's the name of that tube? Clarinet. It's a clarinet. So Fred has a mouthpiece. Inside the mouthpiece there is what we call a vibrating reed. So Fred, would you please let us enjoy what you can? And can you move up the scale?
Yeah, I can do that by lifting my fingers off of the hole so that I shorten the column of air.
You like that? The second wind instrument we have is the saxophone. So Brian, can you do the same things that Fred just did? That sounds pretty good, doesn't it? The last wind instrument we have is the trumpet. And the trumpet, of course, has a mouthpiece. Penny, can you blow air through the mouthpiece? No sound whatsoever. We need to generate a vibration. So could you attach the mouthpiece to the trumpet and blow again? Same thing. So we must have a vibration. So how do you do it, Penny? But you actually do it with the trumpet close to your mouth, right? Go. Isn't that beautiful? Now, how about hearing something from the Science is Fun Quintet? Are you ready? Bravo! Very nice, very nice. How about an encore? Would you like an encore? All right. Hi there, Bucky, and welcome to my lab. I'm so happy to see you here again, and I'm sure you and I would like to ask the audience to give our quintet another round of applause. Bucky, you come with me. Come on with me, Buck. Bucky, I know you've been studying for final exams, and they're coming up pretty soon, right? And Badgers are successful again. They're going to the Copper Bowl. Isn't that neat? I'd like to show you a few experiments, Bucky. And I know you're observant. You've been coming to these Christmas programs for many, many years. Maybe someday you'll graduate, right? No, Bucky. What I'd like to ask you to do, Bucky and everyone else, is to focus your attention on these glass cylinders that have in them colored liquids. I'm going to use a very cold substance called dry ice. Dry ice is a solid that changes to a gas directly without melting. We call that process sublimation. And the temperature is minus 78 degrees Celsius. That's why I use the gloves. Yeah, it's pretty cold. I use the gloves to protect my hands from frostbite. So the sublimation is taking place all the time. We just don't see it because carbon dioxide gas is invisible. So what I'm going to do is take chunks of dry ice and drop them in these cylinders in a very special way. You can see what that special way is. What is it? Am I putting the dry ice in every cylinder? In every other cylinder. And we see bubbles. Those bubbles are the carbon dioxide bubbles, carbon dioxide gas bubbles coming from the sublimation that's taking place. And we see lots of interesting things begin to happen in some of the cylinders. Look in this cylinder here, the color has changed as it has in this cylinder, as it has in that cylinder. Color changes indicate to us that a chemical reaction has taken place. We can also see something coming off the top of the cylinders here. More color changes are taking place as time goes by. And so these chemical changes are indicated by the color change. That sounds pretty straightforward, doesn't it, Bucky? Bucky, I know you've got to study for the finals, but would you like to stay? Can you stay for the rest of this show? Would you like Bucky to stay for this show? All right, Bucky. I have a special place saved for you right over there, just for you. So come on over, have a seat, and enjoy the rest of the festivities that we have on this special occasion. So, are you comfortable, Bucky? All right, he is comfortable. That's good. All right. Now, as we can see, there is something coming off the top of the cylinders where I put the dry ice. What's coming off the top of the cylinders is called, what does it look like? Now, it's not steam. No, steam is invisible. It's called fog, clouds. What it really is, condensed water vapor. The water vapor is condensing on the carbon dioxide that's coming out from the sublimation process as we have seen it. And you see now, we even have more colorful changes indicating to us that a chemical reaction has taken place. So what I'm going to do is reach over and get this plastic dishpan that's empty except for what's in it. Air is invisible too. And what I'm going to do is reach over to where I've been heating some water. It's boiling now. I'm going to use the gloves to protect my hands from the heat, not from the cold. Reach over and put the water in the dishpan. What do you see coming off the top? Steam. No, steam is invisible. You can't see steam. What we're seeing is condensed water vapor. When it's cold outside and you blow your breath on your hand, don't tell me you see steam. You see condensed water vapor. So we're going to take some dry ice now and put the dry ice on. I'm still here. You notice that the fog is moving in a downward direction. That's because carbon dioxide gas is heavier than air. In fact, that's how they make fog in the movies sometimes, by using hot boiling water and dry ice. You also notice that at the beginning of this experiment, the fog or the cloud did not move downward, but it moved upward. And I would like you to think as to why that is so. What is it that's different about the conditions of the experiment now from the beginning of the experiment?
You can make a xylophone at home. You need 6 glasses or glass bottles that are the same. Pour a different amount of water into each bottle. Tap the sides of the bottles with a metal spoon to hear what sounds they make. You can tune your xylophone by adding or removing water from the bottles. Then, create your own music.
What I'm going to do next is take a piece of copper, which is sitting on this tripod, and I'm going to heat the copper using a burner, which I will light. And I want you to see what color the copper is right now and what's going to happen to it as we heat it. Copper at room temperature is metallic, of course. It has its own characteristic appearance, but as we heat it, the copper becomes more reactive. In fact, you can begin to see some color changes on the piece of copper. The color changes are happening because a thin layer of copper oxide is forming on the copper, and the oxygen from the air is combining with the hot copper surface to form that copper oxide. What I'm going to do next is turn off the burner completely, and I'm going to, now it's completely off, and then I'm going to open up this valve, which is connected to a hydrogen cylinder, and I'm going to put the hydrogen on top of the copper oxide. And see, we can change it from copper, there's copper oxide. There's copper and copper oxide. You really never know who might drop into my lab here. We have had a lot of different visits.
Ho, 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 ho! Merry Christmas!
Hello there, Santa, and welcome to my lab.
Thank you. Merry Christmas.
I'm so happy to see you again.
It's good to
I know
see you.
This is a very busy time of the year for you. Did you get my letter?
I sure did.
And the list that was with it?
Oh, it was a long list.
Well, it was, well, did I get any of the things on my list?
Have you been good this year?
I think I've been good. Have I been good?
All right. Let me see what I've got in here.
All right.
Uh-huh.
I'm eagerly awaiting.
Aha! A copper bowl.
A copper bowl. Well, the badges are going to the copper bowl. Thank you very much.
Did you say the Badgers?
Yes, I said the badgers, yes. And the badgers are in the bowl, right? The copper bowl, right? Right, Becky?
Oh, let's see. I think you asked for a musical instrument.
Yes, I did.
How about that?
Yes, that's a nice instrument.
Can you play it?
Can I play it? I don't know. Let's find out. I can try. Let's see. You're supposed to hit those things, right? Is that what you...
I think that's it.
That's it, okay.
Oh, my favorite song! Very good. Very good.
I think I'll quit while I'm ahead here.
Let's see.
I had a few other things on my list.
Well, aha.
Oh, yes, I had this on my list. That's a kind of an interesting object. Let's see, what do we do with it? We'll just give it a spin. We'll try it again. It's kind of wet here, so let's dry this off.
You were better at this when you were younger.
Yes.
Very good. Very good.
Thank you, Santa. You know, in my lab we do a lot of experiments, a lot of different things, and we try to understand why different things do what they do. So I'd like the audience to think about what is going on here when this is given a spin like that, and then, isn't that neat? Huh? You think about that. All right. Thank you very much, Santa.
That copper bowl reminds me of something.
Yes?
You know, Mrs. Claus and I have a lot of copperware up at the North Pole, and over the last 1,000 years, it's become kind of tarnished. Do you know how to get the tarnish off of it?
I can make some suggestions. I mean, it's tarnished like some of this stuff
That's
here.
it.
Yeah, and you'd like it to look clean like this.
Oh,
Like that?
yes.
All right, so
Mrs. Claus would love
all right.
that.
So all you need to do actually is get some salt and some vinegar. And what you do, and you get a couple of cotton balls or some paper towels. You put some salt like so, and then you have the vinegar added like so, okay? And I'll close this off so we don't spill any of it.
Careful.
Careful. And then what we do is we wet the cotton ball and make sure there's some salt on it too, and we just rub it.
Oh, that's working really good.
Not
While you're working on that, I have one more question.
all right?
From Mrs. Claus.
Yes,
She has some hard-boiled eggs in the refrigerator
yes,
and some regular eggs.
yes.
How do you tell the difference? Do you know that?
Yeah, I think so.
That looks
Is
beautiful.
this satisfactory?
Oh,
This, huh?
I can show that to Mrs. Claus.
Yes, you can indeed. Let me see.
Thank you.
Well, I happen to have some eggs here, and actually I have 2 eggs. And let's see if they they look the same.
I
right?
can't tell the difference.
They're about the same size. So suppose I take this one and give it a spin. Look at
That
this.
spins really well.
That spins well. Suppose I take the second one and give it the spin too. That doesn't spin
work.
as well, right? So,
Doesn't spin.
So one way in which you can tell the difference between a hard-boiled egg and a raw egg is to give it this spin test. That's pretty easy to do, right?
Yes.
Now,
How do I know you're telling the truth?
oh, Santa. You want more proof. is
Break
what
it
you
open.
want. Yeah. Break it. Which one should I break? The raw one or the hard-boiled one?
Which one should he break?
Ah,
The raw one.
all right. This is the one that spins. You see that? Okay. So I'll break this one, and you see that this is the hard-boiled one, right? Okay. All right.
You know everything.
This one here, I better break it inside here, right? Well, this was the raw one. All right?
Great. Thank you. I'll tell Mrs. Claus.
Thank you, Santa.
Thank you.
I know your reindeer are probably waiting for you outside, but can you stay for the rest of this program?
I'd love to.
Would you like Santa to stay?
I'd love to. Merry Christmas.
I have a seat saved for you right next to Bucky.
Thank you.
At this time, I would like to call on Fred Juergens to come out and make a very special presentation. So
Well,
here's Fred Juergens.
Thanks. I'd just like to welcome Santa. Thanks for coming, Santa. And just for you, I've prepared a set of special beakers, and I'd like to show you what I'm going to do with them with this glass rod. For you.
That was very nice, Fred. How about an encore, Fred?
Oh, okay. Well, we've got Bucky here, so we ought to have an encore for Bucky, right? That's for you, Bucky.
Thank you very much, Fred. Thank you. You know, we were doing a lot of experiments with bubbles, and I'd like to continue to do some experiments with bubbles that come in a carbonated beverage, such as this one. There are lots of gas molecules pressurized inside this can. I want you to just be quiet and listen and see what you can hear as I open this. Did you hear that? That's the release of the pressure from the carbon dioxide that is inside this can. There's a lot of gas inside this can. In fact, I'm going to show you, try to show you. Let's see what happens. I have a baby bottle here, except that I have replaced the nipple that has a hole in it. I've replaced it with the rubber bulb from a medicine dropper. And I want to show you how strong this rubber bulb is. Let me just take it out here and put it back in. But before I take it out, I'm going to try to inflate it. So, it's a very strong piece of rubber. I put it back in place like so, and then I will take the carbonated beverage and put it in the baby bottle. You see bubbles? Those are carbon dioxide bubbles coming out of the liquid. I fill it all the way to the top, and the next thing I'm going to do is put the screw cap on, tighten it. What should I do next? Oh, you've done this experiment before, huh? Okay, I'm going to shake it and we'll see what happens. There's a big bubble for you, right? This is how much carbonation is inside the carbonated beverage that we have here. Now, what we can do is release the pressure, and of course there's several ways to do that. One is to try to do it fast, and then what will happen? We'll make a mess, right? Or we'll try to do it slowly and see if we can avoid making a mess. And as the pressure is released, you can see that the, oops, some of it dripped out. That's all right. It's all safe to handle. Of course, it's safe to drink. So this is then more about bubbles. Of course, what we want to do now is have some more fun with additional items that we can find around the house, in the kitchen or elsewhere around the house. And what I want to do is show you a few more experiments with bubbles. Here's some water and a straw. Usually we use a straw to drink. What I'm going to do now is use the straw to blow into the water. Just making bubbles, right? But there's nothing to hold the gas that I'm blowing in place. So what I'm going to do is add a little bit of detergent, like that. And again, I'm going to blow gas. And you see now that the soap film holds the bubbles in place. Now there are other ways to make bubbles, and one way would be to take a dish, as I have over here, that you can use to generate some bubbles. And what you do need is some laundry detergent, and then you can add to the laundry detergent some, what am I adding? Baking soda. You put in about the same amount of each and mix them together like so. And then reach out for another household chemical that you might have around, and that is what? Vinegar. So you put the vinegar in, and that's another way of making bubbles. The fizzing that's happening is because the baking soda is combining with the vinegar, which has in it acetic acid, and we've made some bubbles that way. So there still are other ways to make bubbles and to make foam, basically. That's what we're doing. We can take some whipping cream, put that, some of that anyway, in Pilsner like so, and then blow. And all we're doing is introducing gas, in this case, air, to the cream. Of course, there's another way of doing this, right? What's the other way of doing it? Use what? Use a beater. Use a beater, you're right. So that's what I'm going to do. I'm going to take this cream that I have and let you take a good look at it. I have a bowl. I put some cream in. And then I'll reach for my beater, which I happen to have here. And does this look like something that goes on around the house? Yes. I can go even faster. And what happens to the cream when it's whipped like this? It becomes whipped cream, I know that. But what happens to it then? It gets in to be a foam, right? So you can see that it has a different texture and different appearance than it did before. And that's what we have inside ready-made whipped cream like so, except that when we get the cream out, we have the liquid on the inside, and there is a gas inside the can that propels the cream out. So what we end up with is cream. What do we do normally with cream? We eat it, right. Well, let's do a few more experiments with other things that are around the house and around the kitchen. We'll come back to the cream. You know what holds the cream is having a film, just like we had the soap film before, hold the gas inside. So what I'd like to show you is this experiment over here where I have a balloon inside this glass flask that I'm going to now evacuate. It's hooked up to a vacuum pump, and I'm going to get the gas out of this glass vessel. You can watch and see what's happening to the balloon. Is anything interesting happening to the balloon? The balloon is getting bigger. The balloon is getting bigger because the pressure outside the balloon is getting to be less than the pressure inside the balloon. And so the rubber is acting as a barrier to keep the gas inside. So that's one thing we can do. And of course, what happens when I let the air back in? The balloon collapses. Well, goes back to the original shape that it was in. So I'm going to take this off now. I'm going to show you what can be done and what will happen if I take another round-bottomed flask, and into this flask I will put some of this cream. So okay. And the next thing I will do is connect this to the vacuum pump, and you'll watch the cream and see what happens to the cream as we change the pressure on the inside. Anything happening to the cream? It's getting bigger. Now, what do you suppose will happen if I close this off, unplug the vacuum pump, and then let some air in? let's just do it and find out, right? All right, let's get back and do a little bit of more chemistry in our lab by taking a bowl. And in this glass bowl, I have some water, and I want to beat the water, but I don't want to use the same beater I used before because it's got some cream on it. So I have another one here conveniently. And so what we're going to do is simply beat the water. See what happens now? You can, as fast as you can. You all have had this experience, haven't you? Nothing really exciting happens. It gets some bubbles in there, but the bubbles are not held. So what we're going to do next is take some flour. This is wheat flour. Add the wheat flour to the water. Do we do this around the home or not? Yes, we do it all the time. And we beat the flour and the water to make what? To make dough, right. And we can use the dough for a lot of interesting things that we can cook and enjoy. Now, I want you to look carefully at the dough because the dough is doing something very interesting. Can you see how the dough is behaving differently than the water did? Right? The dough is climbing up, right? And then when I stop, it flows down. If I beat it again, so this wheat dough has this interesting behavior that actually anybody who's done any cooking and baking of this sort knows about. So I thought you might be interested in looking at that. All right. What I want to do is mix other household chemicals that we easily find around the house in this cylinder. The first one I'm going to mix is a viscous liquid, which is called what? You can read the label. All right, here it is. I put some honey in. Okay, yum yum is right. Right. And then I will add on top of the honey, I will put some water. And I'll do this carefully. And I have now two liquids that are not miscible with each other. They don't mix with each other, and they have different densities. I can take a third liquid that we have around the house, which is what? What's this one? And I can add oil, olive oil in this case, on top of the water layer. We know that water and oil don't mix, right? So we have 3 layers, and I can take still another liquid that we easily find around the house, and this is rubbing alcohol. So I can take some rubbing alcohol and again add that carefully, not to mix all the liquids together. And you see we end up with 4 layers of liquids that have different densities and do not mix with each other. Actually, the top layer of the rubbing alcohol will mix with the water if one were to take their hand and put it on top like this. Let me do it this way to show you what happens. You see that we have 4 layers now, right? And without spilling this, see if we can mix those. And the alcohol and the water will mix with each other, and the honey and the oil and the water will not. So we started out with 4 layers, and when the different bubbles come out and the layers settle, we'll come and look at this again, and we'll see how many layers we have.
Want to make your own volcano? Here's what you need. powdered laundry detergent, baking soda, vinegar, a plastic glass or dish, and a tray. Add several spoonfuls of laundry detergent and the same amount of baking soda to the glass and mix them together. Pour the vinegar into the glass and watch what happens.
I have a beaker and behind it there are 3 flasks with 3 different liquids in them. I'd like everyone to know that this 1996 Christmas lecture is dedicated to the memory of Professor Hubert Allier, who died last October at age 93. He was truly an international grandmaster of sharing the joy and fun and excitement of doing chemistry with the public at large. And I'd like to dedicate this to him by mixing these chemicals together. Professor Allier taught at Princeton University throughout his career. And these are the Princeton colors. Now I'd like you to focus your attention on this large glass beaker that I have. It has a volume of 4 liters. And if you look at it carefully, you have just learned how big 4 liters is. You can't unlearn it. You may forget it, but you can't unlearn it. And into this beaker, which is empty except for air, and this magnet that is coated with Teflon, sitting on top of a magnetic stirrer, what I'm going to do is mix different liquids that are clear and colorless. And we'll see what happens when these liquids are mixed. Anything exciting happen? It looks like it's the same as this one, but is it? This is a mixture of about 8 or 9 different chemicals, including something we call potassium iodate, hydrogen peroxide, manganese sulfate, malonic acid, potato starch is in there, sulfuric acid is in there. And this yellow color that you see is the color of iodine, what we in the vernacular call iodine. The blue color that you just see here is the color of the iodine combining with the potato starch. And this mixture that has these different chemicals in it continues to oscillate by generating and consuming what's getting generated until one of the original reactants is totally consumed. Now you like that? Now I'd like to ask Fred to give me a hand. Here is Fred with the tall glass tube. This glass tube looks wet on the inside. I have a step stool here that I'm going to stand on. This tube looks wet on the inside because it has a liquid in it. It also has a colorless gas. We can't see it because it's colorless. And what I'm going to do is take the rubber stopper that's on the very top, lift it up after I strike a match so I can drop the lit match into that tube, and we're going to do this in the dark, all right? So I'll strike the match, take the top off. This experiment released energy in the form of light. We saw that. In the form of sound, we heard that too, right? And also there's a deposit of this yellow substance on the inside of the of the tube, that's sulfur. What I'd like to have us do now is to look at this in slow motion and see if we can learn more about this exciting experiment. Again, we won't hear any sound. There's the match being dropped in. There I am trying to get out of the way. All right, let's do another experiment. Actually, let's do this experiment by taking a clear and colorless liquid and mix it with a clear but colored liquid in this very special glass assembly where there is a glass funnel at the top connected to a spiral glass tubing, which then leads to a receiving flask at the bottom. So we'll mix those two liquids together in the dark and we'll see what happens. So let's turn the lights off. This mixture generated light energy, no sound energy, and I can tell you by touching it, it's still at room temperature, so no heat energy. When we mix chemicals together and we generate only light energy, we have something called a chemiluminescent reaction. So the phenomenon of chemiluminescence is what we have just seen here. Of course, just about everyone knows about chemiluminescence because you know about the firefly reaction. The firefly reaction is bioluminescence. It's taking place in a living organism that has a catalyst that makes that reaction go. So let me now look at what I have down here. Excuse me. I have a flask and I have another flask that has some water in it. I'm simply going to dump this water out. It's not big enough, so I'll use another. All right, and now what I'm going to do is mix into this flask two liquids, like so. Here's the first liquid. And here's the second liquid. And then I'll put the rubber stopper on top and swirl it around. We learned today, among other things, that a color change indicates to us that a chemical reaction is taking place. Do you see a color change here? Huh? Is there a change at all? Yeah. We started out with two clear and colorless liquids, and now we have a dark liquid. What else do you see happening here? You see my hand getting tired from doing this, I know that. Well, what else do you see? I see something here. Huh? I see my own reflection here. It's getting shiny, right? The inside of the flask is getting shiny. Now put this down. You can see that. And I would like to show you what I prepared ahead of time before you came in. This one. I'd like to close this very special presentation by reminding you to enjoy doing experiments, to have fun as you do experiments safely, and to remember, no matter what you do, that science is fun. Thank you very much.
You can do some of these experiments at home. Check out the Science is Fun website.